It's a great pleasure and honor for me to introduce you Andy Gordon. So Andy Gordon is, most of you will know him, or otherwise you should know him, from his work on concurrent Haskell. He worked on the SPI calculus, a very important language for security, and he worked on the ambient calculus. Actually, this paper on, I looked it up, his paper on mobile ambience with Luca Cardelli at Fossax 1998, so the very first ETAPS, received more than 2,000 citations. And I think it's the most cited paper, at least of that year, of ETAPS. Actually, for that work with Luca Cardelli, he also received the SIGPlan Most Influential Popple Award paper. He's also well known from SecPal, which is a Microsoft specification language for access control policies. And since a few years, his research has shifted a bit to the direction of probabilistic programming languages. And I'm very happy that he's here today to give us an insight in the research that he does on probabilistic programming. Andy, the floor is yours.
Great. Thank you, Peter. It's terrific to be here at ETAPS. I remember the first one in Lisbon. I remember Amsterdam. It's been fabulous, ETAPS. Today, I'm going to talk about structure and interpretation of probabilistic programs. This is an area I've been working on for the last few years, published at ESOP and Popple, for example, about it. And I'd like to give you an idea of the application area and what the structure of these programs look like. And to begin with, I'm going to do an experiment and show you a particular distribution. And then I'll show you how to write that as a probabilistic program, just as a starter. I mean, the rough idea of probabilistic programs is that they're a bit of code that helps you write probability distributions, and then we can do inference on those distributions to learn parameters and predict missing values, so as to do statistical analysis or to do machine learning at various levels. But the basic thing is you can just use probabilistic programs to represent distribution. So let's start off with the geometric distribution. So this is all about coin flips. So let's flip a coin. We get heads. We flip it again. We get heads. We flip it again. We get heads. We flip it again. We get tails. So we've had 3 heads. So that's the number that we've got, for, the first sample we've got from the distribution. Let's try again. Flip. Oh, it went straight to heads. So that's a 0. Let's try again. Flip. Heads. Tails. So we get a 1. So you get the idea. The geometric distribution is the number of type. To sample from it, you toss a coin, and the sample you get is the number of heads before you get a tail. Very easy. But before I go on, I can't resist pointing out that the coin I was flipping was a euro, and this, I can hardly see it, it's rather small, but this is actually Queen Beatrix of the Netherlands. I have to tell you, back in '99, I had great fun in Amsterdam on the Queen's Day, April the 30th, and that's actually the birthday of her mother, whose name has suddenly eluded me, but it's celebrated by the Dutch. Do you know that? Juliana, yes. So it's a fabulous party, so it's probably you don't want to spend the rest of the month, but I recommend you come back for April the 30th. Great party. I was in Amsterdam. I actually went along in my kilt, and I wore an orange T-shirt, the national colour, and the Dutch were incredibly friendly. It was a really fabulous party, dancing in the streets, this sort of thing, really great thing. I checked it this morning, and I think she abdicated a couple of years ago, a good thing. Does this mean that it's now the King's Day? So is it this, on April the 30th? Okay, there you go, the King's Day. I highly recommend it. So I'm not wearing the orange, but you notice that my distribution is in orange, so I did my best. Okay, so that's the geometric distribution. Flip, 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 hit tails, and then that's your number. So here's how to represent it in a probabilistic programming language. This is a language called Church, which is a probabilistic version of Lisp, of Scheme. So let's see what we've got. So this is the query up here, or rather, MH query is the query, and there's some numbers here about the number of samples to draw. Let's not worry about that. And the form of it is that we make some definitions, some scheme-style definitions of a function, and then a number, and then this is the value that we want to return. And then I've also put a constraint on, because very often in statistical inference and in machine learning, you have a probabilistic model, but then you want to condition it on some observations you've made of the real world. So in this case, what am I doing? I've got a recursive function, geometric, that flips the coin. So flip is a built-in operation that will toss a coin and it will come up with probability P of being heads. And I'm actually calling this function with the probability fixed to being a half. So it's a fair coin. So if it comes up straight away, then we go to 0. Otherwise, we try again and then add 1 to the result. And so that's giving the geometric distribution. So if we stop there, that would be the true geometric distribution like I was showing you on the opening slide. But I add a constraint. So I put it here, I constrain n to be greater than 3. And so if you run this, you can take this code, you can actually go to this website, forestdb.org models-geometric.html. So the Church folks have done a web-based version of Church that uses JavaScript on the browser to implement probabilistic programming. And so you can type this in, and I did this, and you get this as the distribution. So the label there is 4. So that the smallest number we're getting is 4, then 4, 5, 6, 7, and you can see they're getting, there's fewer and fewer of them as the number gets higher. So that's the basic idea of a probabilistic programming language. It's a straightforward deterministic language, but it's being augmented with 3 things: with the ability to draw from distributions, with the ability to specify the distribution, or what it is you're wanting to observe, in this case, the number of heads. And third thing is a constraint. So in fact, I say this again here. Probabilistic programming, you can start with functional languages. There's also lots of logic-based probabilistic languages and also imperative ones. And each of them has some way of adding randomness, some way of adding constraints, and then you say what it is you want to infer. And usually in the context of machine learning, the argument for using these is that that if you use the probabilistic programming language, it has a built-in generic way of doing inference, like of learning the distribution, like I showed on the previous slide, and that the compiler writer has put a lot of effort into doing a good job of inference, and so you as the user, you simply have to define the model in a declarative style, as I just showed you, and then it will do the inference for you. There's many systems. I'm not going to read them all out. The granddaddy is Bugs, that was actually developed in Cambridge in the stats department at Cambridge University back in the 90s. Church, in some ways, sort of reinvigorated the idea of probabilistic programming within the machine learning community, which is curiously very distinct from the statistics community back in about 2008. A system that my work has mostly been based on is called Infer.net. I'll say a bit more about later on, and there's lots of others. And they're doing well. So some recent successes. The last year, a descendant of Church was used to do image recognition in computer vision, and they did a lot better than the competition using code directly written in C, and they got a prize for that at the CVPR conference last year. And then in the commercial world, there's been various big applications of probabilistic programming. And one recent thing that came out last year was the latest version of Microsoft Office, or at least the web-based version of it, has a sort of declutter facility that kind of prioritizes the important mails above less important mails, as opposed to junk, and that was built using the Infer.net system that I'm speaking about. So that was a big rollout to hundreds of millions of users in Office. And in terms of the semantics, the pioneering work was by Dykstra Quote back in the late 70s, early 80s, and then there's also work, Giri in on the probability monad, Claire Jones and Gordon Plotkin, Prakash Panangadan et al., Ramsey and Pfeffer. There's been a line of work, some of which has appeared at the ETAPS conferences on the semantics of probabilistic programming languages. I too have a quote from Dykstra, a great man from Eindhoven. He was professor in Eindhoven before I was born, so that's a long time ago, back in the early 60s. Only do what only you can do. I love this slogan. I put this up for 2 reasons. One is I think it's good life advice. So if you remember anything from this talk, remember this. Don't follow the crowd. Don't follow the crowd. Only do what only you can do. The second reason is more of an excuse, that I want to talk about the general structure of probabilistic programming languages, and the one that I know best is the one that I've worked on with my colleagues over the last few years. So I'm going to use tabular as the vehicle for describing the structure and interpretation of computer programs, probabilistic programs. Okay, so in this talk, what I'm going to do is describe the design of our programming language tabular, And why did we do this at all? Well, we wanted to build a language that would help various sets of users to do statistical modeling and machine learning. And we wanted to make it very easy to write down the models and based on the structure of the data. And so we came up with a number of design choices that are rather different from other probabilistic programming languages, rather different from Church, for instance, or Bugs. And I'll explain why during the course of the lecture. But let me just show you the sets of people you might be after. So at the bottom, there's the high end, the machine learning PhDs, the people who are writing PhDs about some new sampling algorithm for a probabilistic inference. We'd like them to be able to use it, but they're not primarily the people we're after. Then there's people who are like developers who want to use machine learning in their company for various reasons. And we'd definitely like them to be able to use it. And then there's a data scientist, someone who doesn't see themselves as a developer, but they're a statistical expert. They maybe use languages like R, and they're comfortable with the ideas of probability distributions, and we definitely want those people to be able to use our language. And then finally, there's data enthusiast. So this is a person who doesn't see themselves as a specialist in stats, but does care a lot about the structure of their business. And they... so this is maybe someone who's like a doctor in a hospital who's wondering why some of her patients come back after a treatment, others don't. Or maybe a car salesperson who wonders why is it some cars do well in auctions and other ones don't. They've got data. Data is really abundant these days. These are the people who would be very comfortable in spreadsheets like Microsoft Excel. That's where the data is. I would like Tabular to be a language that those kind of people can use to describe their data. So obviously there's way more data enthusiasts than machine learning PhDs. At the same time, these people are less sort of mathematically savvy than machine learning PhDs. So in a way, we've started with a language that probably so far has mainly been used by machine learning PhDs and developers and data scientists, but I'm really trying to go up this, up towards the top of the slide to this larger set of users. And it's a journey. We're not there yet, but we've made some good progress. So Tabular itself, 3 guiding principles I'll bring out. Firstly is that we start from the data. You can't do machine learning or analysis without data. And generally speaking, the data has got a relational form to it. So the key idea of Tabular is that we use the structure of the relational database as a framework for hanging your probabilistic annotations. So that's rather different from the coin flipping I showed earlier, or the geometric query I showed you in Church. The second principle is that we have a way of filling in hidden variables and missing values that are present in the database, and I'll show you that shortly. And finally, we're all about auto-suggesting models based on the structure of the data, and I'll say a bit about that, and that's the part we need much more of before this is going to be fully usable by the data enthusiast. So if you're interested in program synthesis and sort of search and sort of optimization problems, I think this is a good area to get into. Okay, and we got various papers about these about the design of Tabular. Okay. So now let me introduce Tabular by describing the structure of a Bayesian model. And first of all, show it in mathematics, and then I'll show you how to write it in Tabular. Okay, so this is the model for linear regression. So the idea is that we have some points, and we want to fit a line to the points, and the line is going to be parameterized by its slope, which is A, and by its intercept with the y-axis, which is b. And so we could say that the model is that each y is ax plus b plus some noise. And the noise is like the difference, or they call it what do they call it? The residue. No, they don't. The word's going out of my head. But there's not the residue, I've forgotten the word. It's the difference between the actual point on the line and the actual point you're trying to model. And so this is noise. So if we're Bayesian about this, what this means is that we start with some priors about what we think the slope and the intercept and the noise are, and then we're going to update them in the light of experience. And so when people say they're Bayesian, it just means that we're going to update the prior knowledge, and the prior knowledge is expressed as distributions, and the output from inference is going to be further distributions. Other methods maybe would simply give the mean of the updated distributions, but if you're Bayesian, then you return the probability distribution. Residuals, that's the word, not relic, residual. That's the difference between the point and the line. So we've given a rather tight prior on the parameters that they're normally distributed. This is the Gaussian distribution with mean 0 and standard deviation 1. And the noise is also normally distributed with a larger standard deviation 2. So how would we write this in tabular? Well, it would look like this. So this is a tabular program, and tabular has been designed to fit into the style of a spreadsheet. So basically, every tabular program is a spreadsheet or a table within a spreadsheet. That was one of our design goals, because we want data enthusiasts who are already comfortable using spreadsheets just to be able to type these models up within the spreadsheet. And we're also assuming that the structure of the data can be represented as a sort of relational style schema within the spreadsheet. In this case, it's just a single table, and it's called XY, and the actual data that's present are these attributes X and Y. So I'm thinking that the data itself is going to be columns of X values and columns of Y values. But we also declare two parameters that are static, meaning that there's only one of them, not, so that the X, there's columns of X and Y data, but there's only individual A's and B's. So A and B are the two parameters, and we just say that they are Gaussians, and then this is the model for linear regression, and the X column is an input, so we assume it's always present, and then given the X, we're going to predict what the Y is, and we do it via this model here that multiplies X by A, the slope, adds in the intercept B, and we use that as the mean of a Gaussian. So if you draw from a Gaussian with that mean, what you're going to get is a point that's sort of near the point, but not necessarily on it. And we give the standard deviation 2. Okay, so that's a simple example of a model in tabular. Now, so I promised to talk about the structure of probabilistic programs, and I'm going to use this to illustrate just the general structure that almost all probabilistic programs have, almost all Bayesian models have, not just whether they're in tabular, but in any probabilistic programming language. So a key thing is that we have parameters of the model. In this case, it's the slope and the intercept. These parameters could represent other things, and so I'm going to come to an example of skills in a game later on. And there, the parameters are going to be how skillful individual players are. So almost all probabilistic models have parameters, and they have distributions. And so we could write that as the probability of A and B. So we could write that as a probability density function, a joint density on the values of A and B. How likely are they? And then the other part is that we have what's called a sampling distribution, which is a distribution that lets you choose the values to be predicted, the outputs, in this case, the points on the line, given knowledge of the inputs of the model. In this case, it's the x's. So I'm not trying to predict the x's, so they're given as inputs. And they're also a function of, this distribution is also a function of the A and the parameters A and B. And this is sometimes known as the likelihood. So if you see anything about Bayesian reasoning, you'll often see models described as a combination of a distribution over parameters and a likelihood. And in tabular, we'd write them like this. Now, then you have the predictive distribution, which is putting the whole model together. And this is done by an integration, where we integrate out the values of the parameters and multiply the probability of the parameters by the probability of the y's that are the y's given the parameters and the inputs. So that's the sort of official definition of the predictive distribution. If you think about this, if you think about this in operational terms, it's very simple if you don't like the integration. What it means is operationally, to sample from the predictive distribution, you would first of all randomly choose A and B, and you've got your x's fixed. And then the A and B will choose an intercept and a slope, and then you can sample for every x or y given by those A's and B's. And that's the predictive distribution. It's just a way of synthetically generating the data. And so if you take the tabular program, you can run it forward and you'll get the predictive distribution. But that's not very interesting. That's forward running of the model. The interesting part is if you can do inference, if you can condition the model on data that's been observed. So what we say is that if there's no observed outputs, what we have are the prior distributions. And often when you hear prior spoken about in a probabilistic model, they're talking about the prior distribution over the parameters. But then you have the posterior distributions, which is the distributions after you've actually observed some data. So in the example of my coin flipping, the prior was the geometric distribution, And then the posterior is that distribution conditioned on the n being greater than 3. So what I was showing you in the plot at the start, where all the numbers were greater than 3, was the posterior of the predictive distribution. Okay, now a bit about probabilistic inference. So these two gentlemen are the founders of two major schools of probabilistic inference. On the left, we have Stanislav Ulam, who was the first to see that you could use computers to do what he called the Monte Carlo method, which is to do integration by making random choices of values and summing them up. And Church uses sampling methods to do inference. And a great many probabilistic programming systems use sampling of various sorts. And then the representation that Monte Carlo methods used for a distribution is a set of samples. And this method can be slow, but if you let it run long enough, possibly very long, you'll get the right answer. So it's a good sort of gold standard if you're doing inference with a probabilistic programming system. On the other hand, there's message passing. So Judea Pearl, who got the Turing Award in 2011 for his work on probabilistic inference and reasoning about uncertainty and knowledge representation in AI, he invented the idea of message passing, which is where you have a graphical representation of a distribution, and I'll show you this in the next slide. The locality in the graph allows you to do inference by a sort of optimization method where you look at constraints between, you're attempting to find the parameters for distributions for the marginals, i.e. the distribution on a particular sort of variable within the program considered in isolation where you've summed out all the other values. And he has a method where you use the graphical structure of the probability distribution to optimize those distributions. I'll show you this in a moment. This method is fast and it scales really well. So the clutter feature in Office 365 uses message passing. It wouldn't be viable to use sampling, but it's approximate. So it can give the wrong answers. So it's a typical trade-off we have in computer science. But often message passing is great. What's wonderful about a probabilistic programming system, and this applies to tabular, but applies to most or many probabilistic programming languages, is that you've defined the model independently of the mechanism. So having defined the model and you've got some data and you've got some kind of acceptance criteria or measurement of performance of the model, you can first of all test things out using sampling methods, and it maybe take a while, but you can sort of debug it, and then you can use message passing in practice, or use message passing in practice and then measure how badly or well it is doing by falling back on sampling methods. Okay, so here is the graphical representation of my linear regression example. So this is called a Fat2 Graph, and I've got three, not just one, two, but three different interpretations of this for you. So the first one is simply as a probability density function on a distribution over 1, 2, and a number of random variables here based on how many inputs are in my input database. So the circles are random variables. So this is the two parameters A and B, the slope and intercept. This circle is one of the inputs, and this circle or ellipse is one of the outputs. And the oblongs are what are called factors that constrain the random variables. And this box here is called a plate, and this is a common notation in graphical models, which means that we make replicas of the graph within the plate some finite number of times. In this case, it's the size of the input array of points. So there's multiple copies of the part inside the plate. So we can read this as a density function like this, that it's a function of A, B, and the column, the vector of x's, the vector of y's, and it's just given by this product of factors, and that's why these are called Fat2 graphs. So we look at A, particular value of A. So you think about it. So this is saying how likely. Let's see how to interpret this. The idea is you've got a particular value of the slope and the intercept. You've got your x's fixed. and you've got your y's are fixed. And then this is going to tell you how likely is that, how well does that choice of parameters fit that data. And so what you do is you multiply in how likely A is, and it's given by this density function for the Gaussian, and with the 0 and the 1 are the mean and the standard deviation. You know, by evaluating that, you get a number. Same for B, and then you multiply together how likely it is, how likely this variable is, and it's constrained, or sorry, this factor here, which is saying that y, the observed y, is drawn from this Gaussian distribution. So it's very simple and declarative. And that's like the mathematical reading, the pure mathematical reading of this graph as a density function. So the second reading is you can think about this as a program that you can run forward. And this is like the probabilistic programming reading of it. Because you're thinking about this as a functional programmer, say, you could see this is a bit like a map. And these are like assignments, like single assignments to A and B as draws from these distributions. And then this is a map over the input data. For each x, we compute y, and then we output it. So there's that sampling reading, which was what I was describing earlier. And then the third reading is inference. And so this is like Judea Pearl's idea of message passing, that we can try and infer this distribution, or an approximation to this distribution, by fixing a marginal for each of the random variables. So a marginal for B is going to be a particular Gaussian. Its prior is 0, 1, but you're going to update this to be different, so it would shift around, so the mean might go up, the variance might go down. The same for A, and the same for all of these guys. And so there's message passing algorithm. I'm not going to try and get into the details of how it works, but this is how message passing inference works. You start off with priors everywhere, and then you repeatedly iterate, you're constraining the random variables by input data until you hit a fixed point or close to a fixed point. And so the system that we've built on is called infer.net, and this is the core of the Office Cutter, for example. And it's a nice implementation of message passing. And the work that we've done on top of that is looking at various programming languages to make it easier to program. So we did a system called Fun that's based on F# that's part of the Infer.net system. And what I'm going to talk about you today or what I'm telling you about is Tabular, which is a language intended not so much for F# programmers, but for spreadsheet users. Okay, so now, let me tell you another model, which has got a more interesting set of parameters, which I spoke about earlier, the skills. So that we've got the master chief up because this is a model that is used in Xbox Live to matchmake users who want to do multiplayer Halo or other multiplayer games with other gamers that have similar skill levels. And I'm going to explain the model in the context just of two-player games, but it can be generalized to multiplayer games. And so the idea is that we've got a table of players, Alice, Bob, and Cynthia, and we've got a table of matches. And in each row here is saying that player 0, Alice, played player 1, who's Bob, and player 1 lost. So that's saying that Alice lost to Bob, and this row is saying that Bob lost to Cynthia. So a very simple setting. So we start from the data. So then tabular would start from, would then automatically generate the schema of the data. So we're saying that we've got a players table with a column name that has strings in it, and a matches table with a couple of columns, player 1 and 2, that are links back to the players table, just indexes, primary key indexes back to the players table, and win1 is a Boolean saying in each row who has won. So that's the basic schema. And so the idea of tabular is that we augment this with probabilistic annotations to define a model. And so here's the true skill model. So what is the true skill model? I'll say it in words before I show you the tabular, or talk through the tabular. The basic idea is that every player has got a latent skill that is a number that's unknown, and we're going to say that it's drawn from a Gaussian with mean 25 and standard deviation 10. So almost all the skills are going to be between nothing and 50. So that's actually what this row here is saying, that we add a gray latent column to the players table, saying that their skill is a Gaussian. And then the basic idea is when two players meet, we're going to predict who is going to win based on whose skill is greater. But it's a bit more complicated than that, because there's always an element of luck in most games, and also people have good days and bad days. So we have to add a little bit of noise to the skills before we predict who is going to win. So we call those noisy copies of the skills the performances. So in every row of the matches table, we add a couple of extra column values, perf1 and perf2, that are noisy copies of the skills of the two players. And notice here, we've taken player 1 and player 2, and we said player1.skill, which is a reference over to the skill in the players column. And then finally, we make a prediction of who's going to win by asking if the performance of player 1 is greater than the performance of player 2. So that's all there is to the true skill model. So we've written this in tabular. And then now, remember, in the geometric example, they had this syntax, this query syntax in Church to indicate what was to be inferred. So what's the equivalent of that in tabular? Well, we have query by latent column, which is where we start in Excel with the data, and we run the model, and then we fill in the data that was in these latent columns that didn't exist in the concrete database. So we would get back in particular, so the performances get returned as distributions. So these are no longer numbers, they're distributions. So this is Bayesian. Our estimates get returned as distributions with uncertainty parameters, the standard deviation. And we also get the skills back. And in this very simple example, Alice has lost to Bob, and Bob has lost to Cynthia, and so we're getting that reflected in the model, where you can see that the means of the Gaussians have changed. So Alice's skill has gone down to 20, Cynthia's skill has gone up to 29, and Bob's has stayed roughly where they are. The other thing to note is that the prior on the skills was mean 25 and standard deviation, or variance 100, that's the square of the standard deviation. And notice that the variance has gone down. We've got some information, so we're less uncertain than we were. So the bell curves have sort of got sort of narrower than they were. So that's the first way of doing inference, and this corresponds to parameter inference in general Bayesian reasoning. And the second thing is query by missing value. That we've got a row here where Alice is due to meet Cynthia, and we don't know who's going to win. And so tabular will do inference and return this with a Bernoulli 30%. So Bernoulli is a coin flip distribution. So this is saying that we think that she's got a 30%, only a 30% chance of beating Cynthia, which is sort of consistent. Okay, so that was a very basic example. We've built tabular, we've demoed it within Microsoft, and we got various people to use it. And so one of our early users, who admittedly was a machine learning PhD, was quite happy to play with this true skill model, and he was very interested in American college football. And so he built this model here that is a generalization. I won't go into the details of it. It's a generalization of the true skill model, but it's hierarchical in the sense that we don't just have teams. So this is speaking about teams playing each other, but teams are grouped into leagues. So we have a database of leagues, and the idea is that we've got a skill modifier, which is a latent variable attached to the league. And so this is a very powerful idea in statistical modeling, where almost everyone can be grouped in some ways. So schools can be grouped into districts, students can be grouped into classes, companies can be grouped into industries. And often if you're doing a statistical analysis, you'll learn some parameters about the company, but it might also be interesting to learn something about the industry that they belong to. And in this case, what we're doing is learning stuff about the leagues. So basically, based on the performance, some leagues are better than others, and that can be learned from the model. And by taking that into account, you can give better predictions. So, for example, you may have a team. You want to predict how well a team is going to do, and you've seen no plays from that team. But in this model, if you've seen plays from other teams in the same league, then the probabilistic model will kind of share that information and will give you won't just give you an average score for that team, across the whole population. It will give you a sort of average within the league, so you get a bit more information. Another thing I want to show is that he did this plot where he built this model, and then he predicted a ranking of the teams, and then he did a plot of that against human experts. So this is a validation of the model, and so you're getting roughly a straight line that you're seeing there. I don't want to get into the details of this model, but a key point I want to make is that one reason we love putting probabilistic programming inside Excel is that the Excel workbook is a great place to hold everything that matters. You've got your data, That's why we started in Excel. You've got your data, we've got a model as a table, we've got the inference results that get spread out into the sheet, and then you can validate the results, which is very important in statistical analysis. Like this, you want to sort of, well, okay, so this is, your model has predicted something. Do you have any clue whether this is a good prediction or not? So let's validate it against maybe some human experts. And that can be done and plotted within the environment and then saved as a single file. And so we can just mail this around. So it's very convenient. So the data enthusiast, maybe not the machine learning PhD, but the data enthusiast, the doctor or the car salesperson would really like the power of Excel in that respect. So this is one reason that we want to be inside Excel. Here's another model I can talk about. This is a user who is a data scientist who works with the Skype team. She's done the sort of biggest analysis with Tabular so far inside Microsoft. So she was looking at hundreds of millions of users and needed, I think, a 70 gigabyte machine to run models. And the way she actually operated was she built a model using Tabular and used the spreadsheet environment to do the initial prototyping and then extracted out C# code in order to run it. We can be versatile. And these are slides that she used internally. Now, this is not yet in production, but what she was looking at here was detecting abusers on Skype. So if you use Skype, you may have, from time to time, had sort of friend requests come in from people you've never heard of, who maybe are trying to sell you stuff or get you to click on links and so forth. And usually what you do is block them. And you can also report them as abusive. So you can decline their contact request, and you can also block them as abusive. So Skype gathers this data and needs to make a decision about whether to actually shut down those accounts or not, or whether to get a human to look at the account and so forth. Natalia, who was our user, she built a model in Tabular in order to aggregate this data in a Bayesian fashion. And she actually found the Fat2 Graph notation was easier to read than Tabular, so we learned something about that. And so in her presentation, she didn't so much show the Tabular, but showed the Fat2 Graph that she generated. And here you can see part of her analysis, where you can't see very much, I'm afraid, it's kind of small. But this is a histogram of her of the results her model gave, the predictions that they gave about users on Skype and whether or not they were spammers. And her prior was that there was a sort of a 30% chance of them being spammers, which is kind of high. And her model basically, for most of the users, they got pushed to the left, but there's a smallish number, which is still, actually I can't remember the exact number, up there that were confirmed spammers. And the Skype team looked at those and shut down a few thousand accounts based on this analysis. And so that's an example of internal use of Tabular at Microsoft by data scientists. Okay, so let me come back to the Tabular language, and I will go through the core syntax. So our starting point is really just a grammar of schemas. So a schema is a collection of tables. Little t is the name of the table. Big T is the model for the table. And a table has a list of attributes, C1 up to Cn, and they've got types. And types are like this. And mod n is the numbers up to n. So we've got a limited set of dependent types here. So that is just a relational schema, nothing special about that. And so the grammar of Tabular is obtained by adding L's and A's to the grammar, and then L's and A's are given down here. And the L is an indicator of whether a attribute is static or not. So we use static for parameters like the slope and intercept. But if you don't put static, the idea is that the variable is replicated for every row of the table. And then an annotation is either an input, latent, or output. And let's see, an input attribute is data that conditions the model but can't be predicted. A latent variable is an attribute that's not present in the concrete database, like the skill or the performance, but is something that's going to be predicted, so we give it a probabilistic model E. And an output is a column that is present in the concrete database, but may have some missing values we want to predict, like who is going to win a match. So that's the annotations, and then the expressions look like this. There's deterministic functions, there's indirections to other tables, and there's draws from distributions, and a few other things as well. So that's the core syntax of schemas. Then the semantics of schemas is essentially given as a Fat2 Graph, in the way that I've described. And we have papers that describe this in great detail. And I'm not going to try. I think at this conference, you're going to get a lot of inference rules. You're going to get, a lot of logical formulas. And so I decided I wouldn't get too much into the formal details of how we do the semantics. So I've shown you this by example, so that the key thing. So here's here's my running example. So a key thing, if you think about these things as Fat2 graphs, then every table corresponds to a plate in a Fat2 graph. If you think about this as denoting a more conventional probabilistic programming language, then you could think about each table as being a for loop over each row in a table. And then the attributes within the for loop are defining particular values of sort of arrays of variables. The final thing I have not said much about is that on the output columns, these are predictions of values that may be accompanied by actual concrete data. And so in order to condition the model, if a particular observation, like whether somebody is 1 or not, is actually present, like it was in 2 of the rows of my example, then we need to condition the model on that observation. And so we use an observe statement to do that. And semantically speaking, this is conditioning the probability distribution that can be made formal in various ways. See our papers. Beyond the core syntax, so the core syntax is a very simple semantics as a Fat2 graph, but it's a little bit too restrictive, and in particular, it doesn't let you capture common structure in programs that we want to capture. So we introduced some additional features, in particular, function calls and things called indexed expressions. So this is our more general syntax that I've not illustrated so far. So we can use the syntax of tables to define functions. So again, we're keeping in the spirit of spreadsheets. So far I've used this table syntax to define models for tables. We can also use that to define actual functions. And then once we define them, we can call them. So we've got functions and applications, and we also have index models. So let me go through an example of that. So this is a simple statistical analysis to do clustering on eruption times of the Old Faithful geyser in Yellowstone National Park. So I'm going to explain this model that uses this extended syntax. So it's got some function calls here and index models. But before we get into the detail of that, I'll just tell you roughly what it's doing. Is that we've got this data here, and where each point here is representing an eruption, and the x-axis is how long the eruption took. So these ones are taking about 2 minutes, these ones are taking about 4 minutes, and the y-axis is how long you had to wait before that eruption. And you can see that the shorter eruptions you had to wait less, like round about 50 minutes, and the longer ones are a bit higher. So you can see that it forms 2 clusters. So we want to build a model that we can capture this clustering. And the classic way you do that in a probabilistic model is that you have a latent variable on every row that's a 0 or 1 to indicate which of the 2 clusters it belongs to. And that's what I'm doing here. So this is like flipping a coin. So I'm doing this is syntax for drawing from a discrete distribution with a uniform discrete distribution over 0 and 1. So it's basically flipping a fair coin again. So we're back to Queen Beatrix. And then these models here, these rows here, are models of the duration and the time. And those are the things I'm going to explain, because they're actually assembled from function calls and from indexed models. So first of all, functional programming. So here I have, in a sort of spreadsheet-style syntax, a way of defining functions. This is called CG for conjugate Gaussian. So this is referring to, this is a very usable component where we have a hierarchical model of a Gaussian distribution where we have a mean and a precision that are unknown that we want to learn. So these are parameters, and they have a Gaussian and a gamma distribution. A gamma is just an exponential distribution. It's always positive. So the precision is the inverse of the standard of the variance. So it's always positive. And then the output is just a noisy copy. Well, is a Gaussian with mean and this variance. The thing to note is that the mean of mean and prec of mean are inputs to this function, and they have default values 0 and 1. So if I want to use them in order to model, say, the duration, I want one of these models. I want 2 parameters that I'm going to learn. And then each eruption is a sort of noisy copy of that mean. So we're trying to learn the mean of the duration of these events. And so we just do a function call to CG, and then that is going to expand out to this. So we basically have a substitution semantics for functions. So you can understand this entirely at the spreadsheet level. In fact, in our implementation, you can ask for the core form of a tabular model, and it creates a new sheet that expands out all the definitions. And you can see here it's just expanded out the single row into 3 rows where we've made copies of the parameters, and then the duration here is a copy of the output from the function. And so that would be fine, but so far we've not captured the structure of the model, that there should be 2 different means, because there were 2 different clusters, 2 different means for the durations and 2 different means for the elapsed times, the waiting times. So we have a construct called an indexed model that takes a model expression like a function call, and it basically makes an array of copies of all its parameters. And then in the places where it makes use of its parameters, it will index them by a particular variable e-index. So this is the size of the array, and this is the variable to be used to be indexed. And in our case, this is going to be the cluster. So we're going to have an array of 2 values, and we're going to use the cluster to index one or the other. So if we write it like this in our language, so we have a function call, and we index it by the cluster, and then it expands out to this. And so now you see things have changed a little, where the mean and the precision no longer are single Gaussians, but they're arrays of Gaussians. So this is an array comprehension syntax that gives arrays. And then down here, the way to read this is that for every row of the table, it either belongs to one cluster or the other. So if you read it forward, the first thing we do is choose which one we're part of. So we do a draw from this. So we toss a coin to decide which of the 2 clusters we're in. And then down here, when we do the output, we're doing a draw from a Gaussian, and we use the mean of the particular cluster. So there's 2 different means that we might have chosen, and similarly 2 different precisions that we might use. So that's indexed models. So why is that useful? Well, it turns out a whole lot of models use this sort of structure. So something called naive Bayes is a standard model that can be defined using index models. Another model another thing is called Bayes nets, which are a standard way of building classifiers, and they're very naturally defined using index models. Here's another example I want to show, which goes towards the idea that tabular is about auto-generating models. We want our data enthusiasts not to have to think too much about how to define the model. So we'd like to use the structure of the data set to induce a model. So there was a project called Inference a few years ago, and the people who did this, Samir and Tora, their idea was you would start from the schema and then automatically generate a model for the data set. And so they were able to construct a movie recommender in that way. So here you've got a relational database where you've got a table of users, and they've got some demographics like gender and age, table of movies with genres and years, a table of ratings, and each rating has got a link to a particular user, a particular movie, and the score out of 5 that they gave. And they were able to construct this thing, which is a big Fat2 Graph, a more complicated one than you've seen so far. And it was really complicated. I remember talking with him a lot about, what does this mean, how he's saying? This is the sort of informal notation that those folks have got used to, and it works well when you're doing linear regression. But when you scale up to something like these big automatically generated models, it becomes rather hard to understand what all this means. And I remember they were even arguing about exactly where something should go when they were drawing this picture, because they didn't have a good notation for it. And this actually was one of our triggers for designing tabular, because we wanted to capture this sort of structure. And so using index models and these function calls, we can actually do that. So I won't go into the details of this, but suffice to say, we can characterize their project really as probabilistic metaprogramming. That essentially what their project defined was a function, a sort of meta function, that given a relational database would automatically construct this model. And we have this implemented, and so this is a simple way to automatically generate models of data in languages like tabular. Okay, let me see. The final thing I want to spend some time on is R. So when I first got into probabilistic programming a few years ago, R was somehow in a different universe. And in fact, you speak to machine learning people, they didn't really use R. They were keen to use Python and MATLAB and so forth. And so I spoke to machine learning folks for a while, and we worked, to do these things. And I was very happy that we came up with this syntax that would fit in spreadsheets for defining stuff like linear regression. I thought, this is pretty compact, and if you turn this into inference code, it's like 100 times longer. And that's the power of probabilistic programming, that short bits of code in tabular will generate large models in C#. And that's terrific. But then I started reading about R, it's becoming pretty important. And there's something called LM, which is a standard package in R, which lets you define a variety of regression models using a very compact syntax. I was like, oh man, this is pretty bad. I thought this is compact, but look at that. And the beauty of this compact syntax is that it allows the user to quickly play with more complicated models. So X might be a factor, but you may have other columns. So you can just say add Y or add Z, add W, and so forth. And there's various other variations you can do inside R. So that's great. But then even worse, it's like, oh no. They have a lot of sensible defaults. Like you almost always want to have a variable intercept. So the 1 there is standing for the intercept. And so you can just write Y twiddles X, and people often do. And I think actually, even though the machine learning folks and I guess us what are we, programming language people, we didn't really notice this, that they are our language. These R formulas, I think, are the most widely used probabilistic programming language out there. They're not Bayesian, but they do let you define a rich variety of regression models. So we set our task to take this seriously. I mean, it's popular, so I'm trying to make this useful by data enthusiasts. So we figured, how could we add this to tabular, and how would that help? And so we worked out a formal calculus of these regressions and figured out semantics by translation to tabular, and we ended up with Fabula. Such a great name, we had to write a paper. So we did, actually. That's at Popple this year. So Fabula essentially lets you take a tabular model, and so and instead of writing the parameters explicitly, you can just write this simple formula. And okay, so how do the R formulas work? What's their magic? The magic is that you mention the input variables, but almost always what you're wanting to do is multiply the input variable by a coefficient that's a parameter that's going to have a model on it. And the model is often just uninformative. I don't care. I don't know. It's not a 0-1. It's more like a 0, unbounded Gaussian. And you very often also want to have an intercept. So you can write a 1, and it gets a coefficient, and that becomes the intercept. So we've got a translation, and you can look at our paper in detail, but just to show you the idea, just writing that, the x, let me see, the x, right, the x comes out here is multiplied by y0. Y0 is the parameter, so that's the slope. And then y1 is corresponding to that. That's the intercept with the y-axis, so that's just y1. And notice this has got a gigantic variance, so we're very uncertain about what those things are. And then finally, there's some noise. So the noise is this Gaussian, in fact, and its variance is uncertain as well. So we drop that in here as a parameter, a gamma distribution, that we're going to learn how noisy the data is. So from this very short R-style probabilistic program, we get this larger tabular program. So this is Fabula, and it lets you write very compact models in the style of R. Now, I don't have time to go into the details of it. The grammar of the regression calculus is up there. We have a separate paper about it. The thing I do want to show you is this progression. I'm not even going to show you what these models mean exactly, but this is the kind of thing that people like to do in R. And by adding this grammar to Fabula, we can let you do this in our system too, where you've got various different models, or model styles you could have, and the regression calculus term would look like 1 or question mark. This is pure noise. 1 plus x is what we've been seeing. You can also have hierarchical models, like a bit like the leagues that I spoke about earlier. So there's the great rich variety of models you can write. And the other key thing is that most probabilistic programming systems let you give will measure how well the model has fit the data. And this is called the evidence. It's actually the marginal likelihood if you go back to the Bayesian model. But anyway, it's a number, a negative number, and the higher the better. So you can see here is that this is a typical progression where you start off with a sort of a bad model that completely fails the data, and then we add richer structure to it, and this measure gets better. And so this is one way you can interactively, very quickly, build a better model. And so this regression calculus is a nice formalization of R-style formulas that hasn't been done before. I think it's a rich, interesting language that should be added to other probabilistic languages. We've sketched out how to add it to Stan, and it allows a lot of compactification, I think, removal of boilerplate. We actually gone beyond what you can do in R. So it's fully Bayesian, so the results are Bayesian, and we can also define priors within the calculus, which is the sort of thing we're doing there, but I don't have the time to go into that. So here's a slide with the key features of Tabular that I've been going through. It's an unusual probabilistic programming language, but I feel justified in calling this talk structure and interpretation because I think the features that we've designed in Tabular do bring out a lot of common structures in probabilistic programming languages like regression formulas, like index models for things like clustering and classification and recommendation, and so forth. There's a lot of stuff I haven't had time to talk about, but I haven't had time to talk about it. You can ask me questions because I want to finish. That's our key features. You can download it. It's at this URL. We've actually open sourced the core of it. We're planning to open source the Excel part as well before long. But you can download a command line version. It runs on Linux. It runs on pretty much Windows, Macs, everywhere. And we've got a bunch of spreadsheets defining a bunch of things: ranking, regression, clustering, topic modeling, and so forth. And let me finish with this slide. Backing up even to the 19th century, H.G. Wells argued that in the future, which surely is now, that statistical thinking will one day be as necessary for efficient citizenship as the ability to read and write. And that's what many people feel that way. I certainly agree. That's what we've been trying to do with Tabular by letting the spreadsheet be a place where we can do statistical and probabilistic and machine learning work. In the field as a whole, only do what only you can do. At Microsoft Research, Excel is a great target, and but people outside Microsoft Research have been building probabilistic programming systems aimed more at sort of developers and data scientists, and there's some great systems out there that are allowing lots of custom, effective, prize-winning machine learning solutions. There's lots of research challenges. I've put them up there, but I will stop at this point and take questions. Thanks so much for your attention.
Thank you, Andy. Indeed, we have some time for some questions. Yeah, Kim.
Thanks for a very nice presentation. It was very informative. But you have embedded Tabular into Excel, right? I mean, this is what you said. Can you say something about how smooth that is and how it interacts with all the other parts of Excel?
I think it's, let's see, I didn't elaborate this, but Excel these days has a data model, which is a relational database that's built into the system. It's a little separate from the sheets. And we've designed Tabular as a sort of annotation language that describes data held in that database. So in that regard, it fits very well, and we're very happy about that, and that's how we've used it, and we can scale up to large databases because that in-memory database can handle many more rows than the standard spreadsheet thing. On the other thing, and this is work in progress, and I don't have any results yet, I think that Tabular, as it currently, as I've described it, doesn't integrate with the formula language of Excel. And in fact, people quite often use the formula language to do various kinds of Monte Carlo modeling inside Excel. So a thing we're currently working on is adapting Tabular so it can, it makes use of the formula language of Excel. So maybe I can talk about that next year.
Yeah. I mean, the reason why I'm asking is that Peter Sestop from IT University, looking at spreadsheets, a programming language with a formal semantics, trying to actually exploit multi-core because it's a data flow language. So I was just wondering.
Exactly. Yes. No. We've been looking at Peter Sestop's book and exploring how we could adapt some of that to do probabilistic modeling, which is different from what I've described here. But like I say, it would be making use of the formula language more directly.
Any other questions? have a question. Your factor graphs were all acyclic.
That's right.
Is there no need to look for cycles, or are there any fundamental problems if you would have cycles in factored graphs?
Oh, well, yes, they're all directed. However, so the way I describe them, they're directed, and you can sample them forwards. However, for the belief propagation, you consider the graph without the directions, and there, in fact, you do get loops. And so, let's see. So when you have loops in the Fat2 graphs, belief propagation becomes approximate. If there are no loops in the graph, even when you consider it as an acyclic, as an undirected graph, then belief propagation is exact. And however, when you don't have that property, it becomes inexact, and yet it very often will converge. So there are problems, but they seem to come up rarely.
Okay.
The question back.
Other questions? Okay. Opa.
Hi, Andy. So most probabilistic programming languages deal with constructs for static data and models on that static data. In verification, we often look at dynamic models like Markov chains or hidden Markov models and so on. Isn't there a need in the machine learning community to look at more dynamic models in these probabilistic programming applications?
Yes, yes, indeed. So I've not emphasized it here, but a lot of machine learning models in the church family are actually are sequential. So there's things called hidden Markov models where you have which is essentially a probabilistic automata that will unfold some number of times. So in tabular, my tables are all kind of, each row is generated independently, but in other probabilistic languages, you can arrange for them to be generated in sequence, and so you get more of a Markov chain structure within the probabilistic model. So there's one recommendation I would make is that Anglican is something to look at. Anglican is a project at Oxford by Frank Wood, and they've really emphasized what's called sequential Monte Carlo methods, which are perfect for time series, and that might be modeled by Markov chains, for example.
No further questions? Then I would like to thank the speaker again and have a small token of appreciation. Thank you very much.
Thanks to you, speaker.